Hi, this is the final project for the course EEE 6512 Image Processing and Computer Vision at University of Florida. The name of my project is Handwritten Digit Recognition using Deep Learning. So, first of all, I would like to give you an overview of my project. Why do we require handwritten digit recognition? What's the need for that? Secondly, what are the various methods that are already present to do this thing? Third, the overview of the MNIST dataset that I'll be using to explore machine learning algorithms and deep learning algorithms and compare their accuracy for the prediction of the correct digit and its modeling and data and pre-processing. Third, the handwritten digit recognition using machine learning using the commonly used algorithm like random forest classifiers, the k-nearest neighbors, support vector machines, etc. And then the main topic of this presentation, that is the handwritten digit recognition using deep learning. I'll be using the convolutional neural network using Keras and Theano as the backend, and then the references and the demo. So the question arises, why do we even require handwritten digit recognition? Well, you see that nowadays you are using handwritten digit recognition almost everywhere, like the data entry for your business documents like the checks, passports, invoice, bank statements, even sending your mails, couriers, everything employs some sort of a digit recognition or character recognition so that the human labor can be decreased. You have like automatic number plate recognition using, say, videos, image processing and stuff, and also the assistive technology for the visually impaired users. So what are the current methods that are present for the handwritten digit recognition? In terms of, say, machine learning, we have, let's explore. In machine learning, we'll explore using these three techniques. First is the random forest classifier, then the support vector machine, and then the k-nearest neighbors. And the tools used will be like scikit-learn, tf-learn, scipy-image, etc. For the deep learning, we'll be exploring the convolutional neural networks along with the tools Keras, Theano as the backend, and maybe TensorFlow by Google and PyBrains, etc. So first of all, the overview of the MNIST dataset, data modeling and pre-processing. As you know that for each and every machine learning algorithm, deep learning algorithm, artificially intelligent neural networks, the data is the biggest thing. Without data, these algorithms cannot work. They require huge chunks of data, and for data, only to having the data is not enough. You need to have data that is in a particular format. You need to format the data so that you can easily take that data, import that data, and make your algorithm work on that. So MNIST dataset, what is it? It's basically a subset of the larger NIST dataset. It contains 70,000 examples of handwritten digits divided as training sets of 60,000 examples and a test set of 10,000 examples along with the labels. So the MNIST dataset is available in basically 4 files: training set images, training set labels, test set images, and test set labels. So the reading training set images file, how is it means? How do you read the training set images file? For that, you particularly require, first of all, the format in which the data has been provided. So the first row actually for the data has the magic number. This number 2051 actually denotes whether it's a image file or a label file. For label file, this number is different. For image file, this number is different. We'll just come to this magic number in a while. Then we have in the second row this number 60,000. That is the total number of images. So in the training set images, we always want to train our classifier with as much as examples that we can, so as to make its prediction much more closer to, say, 100%. That's the ideal case, but we want to use that. Next is the number of rows and the number of columns. So like MNIST dataset is provided as a array of, or say rows of 784D array, and then those pixels You cannot just make an image out of that, so you require to first convert it into 28 by 28 matrix, and then you can form a grayscale image using that matrix. And then you have the number of pixels along with the which are like unsigned byte. That's the format of that. So what's the magic number? The first table shows you the format of the magic number. It is basically 4 bytes of data. First 2 bytes are zeros, that denotes that it's a magic number. The third byte is the data type. Data type can be anything like unsigned byte, signed byte, short, integer type, float, double, and corresponding values for that. And then the last byte is the dimensions, whether it's a 2D matrix, 3D matrix, or anything. So let's consider an example. Here you can see that for the previous data that we have a magic number of 00000803. So if we have this and put this into this table, we see that first 2 bytes 00, and then the data type is 08, which means it is unsigned byte. Is it? Yes, it is. And then the dimension, that is 3 by 3. Similarly, reading the training set labels. In the training set labels, it's like it has no number of rows or columns data, but rest of the data is almost similar, like 32-bit integer, which is the magic number 2049. This 2049 number is always the same for each of them. And then you have the number of items, that is 60,000. So the number of labels should always match the total number of image or the pixel data. Similarly is the case for reading the test set images and test set labels. Next comes handwritten digit recognition using machine learning. So in machine learning there are 2 times that we usually define. First is the training time, that is the amount of time required to train a classifier so as to make predictions. And the second is the testing time, when you actually test your classifier, that how well it has been trained and how well it can make predictions, or how accurate is its predictions for the testing data. Then some of the commonly used machine learning algorithms are RFC, KNN, and SVM. So now we'll go into somewhat depth of all of them. Firstly is the random forest classifier. The random forest classifier basically works using a huge collection of decorrelated decision trees. In this, the training data forms a matrix as input, and using this matrix a large number of new matrices with the random elements are created. Using each of these matrices, a corresponding decision tree is formed for each and every matrix, and then when the testing data is input, all the decision trees classify the input test data individually and predict the class to which the input belongs. Let's see an example. Suppose this is a matrix S where we have feature A of the first example, feature B of the nth example, and so on. We have to form the new matrix that has the random amount of data, which is basically this data but in the randomized form. So say each of the matrix is a decision tree. So using these decision tree, you input the test data here and you actually try to make predictions that to which class does the input data belongs. Say the first decision tree says that the data belongs to class 1, second says to class 3, then to class 2, then to class 1. If you just see from this example, you can see that class 1 appears twice, that is the probability of class 1 appearing is more than the rest of the classes. So it means that the basic prediction is it's more probably the class 1. Next comes the k-nearest neighbors. The k-nearest neighbors works by calculating the Euclidean or the Hamming distance of the input under test from the training inputs. So it's like the value of k is defined in the code itself, where you can define the number of nearest neighbors. K is the number of the nearest neighbors that you want to compare with, and then calculate the distance. The class that gets the maximum votes, that is the more number of data points close to the data point under test, the testing data is predicted to belong to that class. So the basic formula for calculating Euclidean distance is given as below. Let's see the working of the KNN. Initially, let us say that we have 2 classes of data. one is class A and one is class of consisting of O's. Let us consider that k is 3. We usually try to take k as an odd number because having an even number can cause a confusion, because if, say for example, if k is 2 and we want to have two elements which are pretty near to C and make a prediction, so it can be this A and this O only. So that way C won't lie in either of the classes or in both of the classes, which is not possible. So we always usually try to have the value of k as an odd number. So see, here k is 3, so we see that which are the three elements that are very near to that, means very near to C. So we see that 2 O's and 1 A has the smallest distance to C. So since the probability of C being a part of classes O is more because of the more number of votes, so it's more probable that it's a part of class O. Next comes the support vector machine. Support vector machine is basically a binary classifier that classifies amongst the two classes and comes up with the one that is best. It works by calculating the best hyperplane that can be formed to differentiate between the two known classes. So the hyperplane is said to be the best when it has the equal amount of margins from both the classes. So look, for example, let's say that there are two classes. One class is denoted by blue dots and the other class is denoted by red dots. So the best hyperplane would be that has equal amount of distance from the red dots as well as the blue dots. So let us say that this is the best hyperplane. So that means that this line divides the blue and the red dots, that is the two classes. So let us say that there is some point here. So this means that this point has more probability of being a part of class with the red dots rather than the blue ones. So let's see the comparison till now. So we have seen that for the trained classifier accuracy, for the random forest classifier it's 99.7% and accuracy on test images is 96.89%, which is not bad. For the k nearest neighbors, we have trained classifier accuracy is 97.88% and accuracy on test images is 96.67%. For the support vector machine or the supervised vector classifier, the trained classifier accuracy is 99.91%, which is pretty good, and accuracy on the test images is 97.91%, which is also good. But the thing is that we see that there is still an error of 2 to 3 or 4%, and it's like even if you have an error of 2%, so it can be like instead of sending a mail or an envelope to an address 100, if it predicts that 1 for an 8 for that 2% of error, so your letter say is going for an address 100, it can be mistakenly going to an address of 800. That's not possible. That we don't want. So let's see what the deep learning offers us. So handwritten digit recognition using deep learning. Here we'll be exploring the convolutional neural networks using Keras tools and as well as the Theano as the backend. So let's first understand some of the basics of convolutional neural networks. So convolutional neural networks are made up of neurons that have learnable weights and biases. Each neuron receives some input and performs a dot product and optionally follows it with a non-linearity. The whole network expresses a single differentiable score function from the raw image pixels on one end to the class scores at the other end. So it basically uses a loss function. It can be like SVM, or most probably most widely used is the softmax function. In the convolutional neural network, the input consists of the image data. In our case, it will be the MNIST data, which is 28 by 28 matrix, and then the layer of ConNet have the neurons arranged in basically 3 dimensions, that is depth, height and width. So say we have the input data which is 28 cross 28 because of 784D array, and we want to convert it to grayscale image. So it comes to 28 cross 28. So according to the width, height and depth, it will be like 28 cross 28 cross 3 because it's a 3 cross 3 matrix. So we get all the 3 dimensions, that is the width, height and the depth, 28, 28 and 3. So let's see what are the layers of the convolutional neural networks. There are basically three layers. First is the input layer, which holds the raw pixel values, which we say 28, 28 and 3 because of the width, height and the depth. And then is the convolutional layer, which computes the output of the neurons that are connected to the local regions in each input, each computing a dot product between their weights and a small region they are connected to in the input volume. So this might result in a volume such as 28 cross 28 cross 20, where 20 is the number of filters. So you basically employ some filters in that. So this filter value is not fixed. You can use maybe 50 filters, 100 filters, but there is obviously a limit on how much you can use, because after some time the accuracy will saturate. So it doesn't make sense to use like 500 filters at the very starting of the very first layer. So you have to choose that. Then comes the rectified linear unit, and this basically applies an element-wise activation function such as max 0 cross x and thresholds at 0, which leaves the size of the volume unchanged. So we use this function basically because we know that we have the convolutional neural network with the back propagation. So during the back propagation there might be some distortion in the data, and the data might get somewhat distorted. We don't want that. So to avoid that thing and to keep the data as much as constant, the pixel values as much as constant, and we use the rectified linear unit. Then we use the pooling layer. So once we have got everything, we have the pixels with the greatest intensity. Now we want to make the image again. So we do the pooling and make the image again, and then again implement another layer of convolutional ReLU and the pooling layer. Then comes the fully connected layer. Here we compute the class scores, that is, we have classes like from 0 to 9 for the 10 digits, and then we actually compute the class scores, and this results in the volume of size maybe 1 cross 1 cross 10. Let's see how it works practically. So here we give the MNIST data, which is a 784D array of pixels converted to 28 cross 28 to form the image, and cross 3 as well for the 3D matrix. So now first of all we get to the convolutional layer, ReLU layer and the pooling layer. This is the first set of layers. So in this code we have basically 3 set of layers to make it like deep learning, and you can add many more layers, but it doesn't make sense to add say 10 layers or 20 layers to, you might be thinking, yeah, you can increase accuracy, but that's not the case. In some cases it might work, but usually it won't, because at some point the accuracy will saturate. So when you have the convolutional neural network, here you first define the 2D convolutional layer with 20 filters, and then the rectified linear unit, and then the 2D max pooling with the pool size. So what this convolutional layer does is that it has a 5 cross 5 window that slides across each of the pixels, and in that 5 cross 5 window, if there is the maximum value of the pixel, so this picks the maximum value of the pixel, passes through the ReLU function and makes this point, say. So using all the maximum values, you again reform the image of all maximum values in the pooling layer, and again apply the convolutional layer with say more number of filters to actually get the difference between the different images and see that where it matches. So then you again apply the second layer and the pooling layer, and then you finally connect the fully connected layer with say 500 neurons, and then you get the output, which is in the form of predictions like which class it belongs to. So let's see the accuracy for the convolutional neural network. I've been able to get a trained classifier accuracy of 99.98% and an accuracy on the test images for 98.72%. Although I have also worked with TensorFlow by Google, and I could get accuracy of 99.70%, which was pretty good. So we can see that using the machine learning, the accuracy was pretty nearby, and using the deep learning it has risen much. I would like to thank Professor Dapang Oliver Wu for providing me this opportunity to present my project, and now it's references for my project, and then let's go for the demo. It's demo time. Hi, welcome to the part 2 of my project, Handwritten Digit Recognition using Deep Learning. Till now we have seen all the theoretical concepts. Let's first have a look on the code before going for the demo. So this is firstly, we have to load the data. So we have the data in these 4 files: images, labels, training and testing. So using this code, we particularly I have defined a class along with some functions that take this data, and then I read that if there is magic number 2049 there. Remember that in the slides I defined that if the magic number is 2049, that means it's testing or training labels, and if the magic number is 2051, then it's testing or training images. So if it's the magic number is not equal to 2049, that means it's something else and it should not read it. And similarly for the case for 2051. But if it's not the case, then it should read the data, and this function returns the images and the labels. That's what we want. Now let's have a look at the random forest classifier code. So I have just used the random forest classifier from the scikit-learn. So I just import the MNIST data, and then I divide it into parts like training images and the training labels, and then the testing images and the testing labels, and convert them to the NumPy array. It's basically converting the data into the arrays so that you can modify them and work with them. So now first of all, to train my own classifier, I have used a function from scikit-learn, that is cross validation, which does the training, test and split. Cross validation is basically a class under the matrix which has a function defined for training, testing and splitting the data into the training and testing sets. So here I input the training data and the training labels, and then the test size, and the test size is basically like what percentage of the whole data do you want to test your trained classifier on. For example, we have 60,000 images as the input training data and training images as well as the labels. So what 0.1 means that I am using 50,000 images to train my classifier, and the rest 10,000 images, that is the 10%, I am using those images to actually test my trained classifier to see that how well it has been trained. So I am using then the random forest classifier with 100 estimators and 10 number of jobs. You can define this easily, and then I fit the data and pickle the data and then make predictions on that. Similarly for the k nearest neighbors, I do the same thing. In every code I have pickled the data so that I pickled the trained classifier so that I don't have to spend time training the classifier again and again in this part. So I have pickled the data and I am just reading that data, and based on that I am taking the input testing images here and making predictions on the testing data, that how accurate that is. Similarly for the support vector machine, I am using the similar approach. So I am using the support vector machine here, SVM classifier, and then I am pickling the data and then getting the score and the prediction and the accuracy. For the MNIST, convolutional neural network, that is part of the deep learning or the artificial intelligence, I have defined a class which has a function build. Build basically means to build the model. First of all, we need to build the model on which the convolutional neural network will work. So I am using a sequential model, and then I first create the first set of convolutional ReLU and the pool layer. In the first layer I am defining 20 filters that will be used for the convolution that have the size of 5 cross 5, that is 5 by 5 window size, and I have kept the border same. Then I am using the activation function, and then I am doing the max pooling for the size 2 cross 2. Then I have similar second set of convolutional ReLU and pooling layer, but in this the number of filters is 50, which is greater than the previous layer, and in the third layer I have the size 100. Now for the final layer, which is the fully connected layer along with the ReLU layer, I am using 500 neurons that make the fully connected layer, and then use the activation function. After that, I am doing the softmax classifier. I am using the softmax classifier to make the classification on the which type of class does the data that I get at the output belongs to, and then I can make the predictions on base of that. In this code, I am just calling that model, and then using the SGD function, I am using it as an optimizer, and then I am building the data, providing input data, that is width, height, depth, and classes, and everything else. And then I can just fit the data, evaluate for the loss and accuracy, and I am using batch sizes of 128 and verbose 1, and I can just get the accuracy and then pickle the data and then just show some of the predictions in form of images. Now let's head to the demo. Since I am doing my demo on the CPU, so it takes a lot of time to run the code. So I have already pickled the train classifier, and I have already run the code just now, which has made the predictions. So this is the code for the running code for the SVM. So first of all, it loads the MNIST data, trains the data, then loads the training data, testing data, prepares the classifier. SVM classifier has these features: gamma is 0.1, and I am using the polynomial kernel, which provides us with the maximum amount of accuracy. And then I pickle the classifier and calculate the accuracy of the train classifier. So as you can see, I was able to get SVM train classifier accuracy of 99.8%, which is pretty good. And the predictive values, some of the predictive values are these are the random values. So it's like 7, 2, 1. These were the predicted values. Then I show the confusion matrix. Confusion matrix basically tells that corresponding to each and every digit, what was the accuracy percentage. So like for this number corresponds to 0 cross 0, 0 and 0. So it means for predicting 0, it has an accuracy of 97.2%. So finally we see that accuracy of the classifier on test images is 97.91%. Similarly, if we go ahead, you can see this is the RFC, that is the random forest classifier. So for this I get the accuracy of 99.683%, which is pretty good for the train classifier. And when I see the confusion matrix, and after that I get the accuracy of the classifier on the test images, which is 96.89%. Similarly, going on, I have the k nearest neighbor. In the k nearest neighbor, I use n neighbor 5 and algorithm auto and number of jobs 10, and then I have got the train classifier accuracy of 97.9%, and the confusion matrix, and the accuracy of the classifier on the test images is 96.67%. Now further going to the CNN part. So here is the CNN part. So it basically loads MNIST data, converts the 784D array into 28 cross 28 cross 3 matrix, and then prepares the classifier, converting the labels to the vectors, compiling the models, and then building the first convolutional layer, building the second convolutional layer, building the third convolutional layer, building the fully connected layer with 500 neurons, and then I get some of the predictions on the test images. And you can see the image like this is a 9 and it predicts it's 9. This is the image that is formed from the 28 cross 28 matrix, which is in grayscale, and this is the actual prediction that was made for this number. Similarly, we can see some more examples. So I hope you enjoyed the demo, and thank you.